Hi again, AP Calc students. Time for lesson 7.4, and that's on the lengths of curves. This is kind of a cool lesson in that we've been using calculus to help us figure out areas and volumes, integrals especially to help us do that. In this lesson we're going to use calculus to help us figure out lengths of curves, and especially curvy curves, not just straight line curves. So that's kind of neat. Anyway, it's all based on this idea here that you can see. I think you can picture here, as we can see on this diagram, that if we have a curvy line, we can zoom in on any one part of that curve, and we could kind of make a little right triangle out of all this. And if we thought about the x and y legs of this right triangle, we could really think of that as the change in x and the change in y. In calculus, of course, we call that dx and dy. So certainly this length of this hypotenuse could be represented like that, the square root of dx squared plus dy squared. Now we're going to use some calculus now to help us figure out what the total length of this curve is. I think you'll be able to recognize this on our next formula that we see. So here it is, the length of a smooth curve. You see over here the length of all these little hypotenuses, if you will. Anyway, if a smooth curve begins at AC, so that would be way over here, that's a coordinate, ends at BD, the length of the curve is represented by this. So here's if we have some function of x, this is what we'll mostly have. Notice what we'll be taking is really the derivative of that function. There's that dy over dx. Square root of that, 1 plus that derivative squared from a to b. The a to b here will be certain x coordinates. This formula is basically the same. This would be one we would use if the line was described or solved in terms of x equals something. And then our upper and lower bound would be y values. So there's the formulas. We'll use those. Pretty sure that formula is on your spark chart as well. But we'll use these now in an example we're going to do next. So we'd like to try to find the length of the curve, y equals x minus 1 to the 3/2 power from x equals 1 to x equals 5. Well, the first thing we'd like to do, of course, in this case is find what the derivative is, because that's what we need to use in this particular formula. So dy over dx, here's one where we have to use our chain rule, if you remember. So I'm going to have to take 3/2 times x minus 1. My power has to decrease by 1, and so that's actually going to be to the 1/2 power, like that. Well, now let's plug this into the formula. So I have the integral. My integral will go from 1 to 5, like the problem tells us, and then it's the square root of 1 plus 3/2 x minus 1 to the 1/2 dx, like this. And could we do some simplifying of this way? I think we could. Oh, and I forgot about that I also have to square this. Sorry about that. It's the derivative squared, so I have to get that little square in there. Sorry about that. So now when I simplify this, it's a little bit better. So from 1 to 5, I still have a square root here, but it's really going to end up to be 1 plus. Now when I square this whole expression right here, I do have to square the 3/2, and then I also have to square this expression. Well, when I square the 3/2, that's going to give me 9/4. When I square this other expression, the 2 and the 1/2, 2 times 1/2 of course is 1, that cancels out. So I'm just going to have x minus 1, like that. Now I think you can see we could simplify this to some degree. I can distribute this 9/4, so I'd get 9/4 x minus 9/4, and so 1 minus 9/4, so that would be 4/4 minus 9/4 is going to give me negative 5/4. So what this is going to boil down to is an integral that looks like this. 9/4 x, and then I said minus 5/4 when I combine the number parts together. Notice I got rid of the square root, but we know by now that the square root is the 1/2 power, like that. Now this is one that we could do analytically pretty much. I'm going to bypass a couple steps to show you what it would be. But again, antiderivative of 1/2 would have to be something to the 3/2 power. So it's actually going to end up to be 4/9 times 2/3, and then what we have in the parentheses here, 9/4 x minus 5/4. Remember, our power gets bigger by 1, so 1 bigger than 1/2 is 3/2, and then I want to evaluate that between 5 and 1. So it lets you kind of ponder how I came up with all those numbers there. It's nothing more than taking the integral of something, but also implies the chain rule as well. Remember, if I take the derivative of all this stuff, I should be able to get back to this. That's a good way to test. Alright, anyway, either evaluating this analytically or in your calculator, and I'll show you on the calculator what it would look like here in a second. I think this should end up to be about 9.07. Whatever the units are, sometimes the problem will give you that, oftentimes not. But again, kind of cool because that's the length of that curve, not the area underneath or the volume formed by making a revolution of some sort. That's the actual length of that curve. Now we can verify this on our calculator. I graphed the original function right here, and so you can see what that looks like on the graph. Just looks like a nice curve like that. Now when you actually try to figure this out, remember to use the formula when you use your integral. The way this calculator of mine does actually draws out the integral. You can use that fn int option on your calculator as well. But make sure to put in not the original function, but use that formula. When you find that integral, sure enough, it ends up to be about 9.07. And lastly, thought you might enjoy these cats doing this interpretive dance as they were trying to find arc length of a curve. So thanks for watching, and we'll see you guys in class.